Today we want to discuss the structure of benzene. Before entering into the explanation, we want to know some basic concepts of benzene. First of all, you think about the isolation of benzene, first isolated by Michael Faraday in 1825. Benzene can be prepared from sodium benzoate and soda lime, as well as from coal gas, along with that from light oil, again from petroleum, and the most important process is from acetylene. We will not explain the preparation methods because we are focusing on the structure of benzene. I think you have studied about these methods of preparation of benzene. Next is, benzene is a very good solvent. Along with petrol, it is used as a motor fuel, starting material for many substances like dyes, drugs, plastics, perfumes, explosives, and maleic acid. I have already told you that this class is for the structure of benzene. So you listen carefully because we want to study the historical development of structure of benzene, and finally we will get the updated knowledge about the structure of benzene. So before that, we want to know something about benzene. You see, in benzene, for saturation, 8 hydrogen atoms are required. So benzene is expected to show unsaturation. So here you may have some doubts regarding the number of hydrogen atoms. You listen, comparing this formula C6H6 with the corresponding alkane having 6 carbon atom, that is C6H14, is clear. That means for getting saturated alkane, we want 8 more hydrogen atoms. That's why we are telling like this. This benzene is expected to show unsaturation. Benzene adds only 6 atoms of hydrogen or halogens. Benzene forms triozonide. That is also familiar to you. Ozonization. Reaction with the ozone, ozonolysis. I think it is clear to you now because we are studied in alkenes. Okay. This indicates existence of 3 double bonds in benzene. These facts prove that there are 3 double bonds in benzene. Based on the assumptions of certain scientists, 3 structures were derived for benzene containing double bonds or triple bond, whatever be. In the light of explanation, we can reject these 3 structures. Okay. One more thing. Benzene is resistant to the oxidation by alkaline cheminophore. Reaction between an alkene and cheminophore is a test for unsaturation also, Clear? Cheminophore is a very strong oxidizing agent also. But in the case of benzene, it is resistant to the oxidation by alkaline cheminophore. There is no smooth reaction between alkaline cheminophore and benzene. Okay. And one more thing, if unsaturation is present, benzene should give addition reactions. Instead of addition reactions, benzene gives substitution reactions with the halogens mainly. And one more thing, unsaturation in benzene is different from the normal unsaturation. Normally, if you are hearing unsaturation, you are getting the concept of alkenes. CH2 double bond CH2, CH3 CH double bond CH2, and so on. The unsaturation in benzene is different from the normal unsaturation that is seen in alkenes. Dear friends, one monosubstituted derivative indicates identical nature of all the 6 hydrogen atoms. Is clear now? So in benzene, 6 hydrogen atoms are there. All these 6 hydrogen atoms are identical because only one monosubstituted derivative is obtained at a time. And one more thing, during the development of structure of benzene, 3 ring structures were possible. You can see the 3 ring structures one by one. And the final one, that is called Kekule structure. Kekule structure explains 3 disubstituted products, equivalence of all carbon and hydrogen atoms, addition of 6 hydrogen and chlorine, 3 molecules of ozone synthesis from acetylene. These facts could be explained by Kekule structure. You listen one by one. 3 disubstituted products are possible by using this Kekule structure. At the same time, equivalence of all carbon and hydrogen atoms. All carbon in benzene and all hydrogen in benzene are equivalent. Addition of 6 hydrogen and 6 chlorine is possible. That means a type of unsaturation is there in benzene. Is it clear? Then 3 molecules of ozone can be added here. That means ozonolysis is possible. Ozonization is possible. And one more thing, this benzene can be synthesized from acetylene. CH triple bond CH, the first alkyne, that is ethine. So from ethane we can prepare benzene. So all these facts could be explained by Kekule structure. But listen, some failures are there for this Kekule formula. What are the objections? Listen one by one. Listen. Look here, this Kekule structure could not explain the stability of benzene. That means benzene is highly stable. Even though double bonds are present, there is a peculiar stability for benzene. This stability could not be explained by Kekule formula. And one more thing, it could not explain the peculiar nature of double bonds. A special type of double bond is present in benzene. This Kekule structure could not explain the special nature of double bonds in benzene. Next one, existence of only one orthoisomer could not be explained by this Kekule structure. Only one orthoisomer is possible. That means either 1,2 or 1,6. Simultaneously, you don't consider 1,2 and 1,6. That means two ortho disubstitution products are not possible. Whereas only one orthoisomer is actually existing. So it could not be explained by this phenomenon, could not be explained by this Kekule structure. Next one, why substitution rather than addition? There is no answer for this question by Kekule. So Kekule could not explain the more substitution reaction than the addition reactions of benzene. But listen, later he suggested that there is a special mechanism in benzene. There is an oscillation of single bond and double bond. For half time there is a type of single bond character, and then in the next half time there is a double bond character. Again there is a single bond character, again there is a double bond character. That means there is an oscillation of single bond and double bond. He could explain this. This was referred to as the Kekule's dynamic formula of benzene. It's clear now. This oscillatory motion, oscillation between single bond and double bonds, put forward a special type of structure for benzene, and that is referred to as the Kekule's dynamic formula of benzene. Two scientists, Levin and Kekule, in 1932 supported the dynamic formula by the ozonolysis of orthoxylene. So orthoxylene can be ozonized. Kekule's dynamic formula got support from the work of Levin and Kekule. They obtained glyoxal, methyl glyoxal and dimethyl glyoxal from the ozonolysis of orthoxylene. You should listen the reaction between xylene, orthoxylene and ozone. So you may get an intermediate product that on hydrolysis you get what? Glyoxal, methyl glyoxal and so on. So there is a support for what? Support for the dynamic formula of benzene by Kekule. Okay. Along with that, so many scientists could put forward many structures for benzene. So you should listen the structures of benzene one by one. First of all, cross diagonal formula. Next one, Dewar's parallel formula. The other one, Leidenberg's prism formula. Next is Baer and Armstrong's centric formula. Next is very important, that is Thales' partial valency formula. Cross introduced his diagonal formula in 1867, which explained the simultaneous formation of ortho and para isomer. Whereas Dewar in 1867 suggested formula for benzene, which had its support from the formation of benzoquinone by electrolytic oxidation of benzene. Leidenberg's prism formula represented a stable structure, but as there was no unsaturation in it, it did not find favor. It is discarded. Baer proved that hexahydrobenzene and cyclohexane were identical and hence supported a 6-carbon atom ring for benzene. Thales applied his theory of partial valency to the benzene problem in 1899 and gave the formula. Thales' formula could explain the stability of benzene, no doubt, and also eliminated the difference between 1:2 and 1:6 positions, 1,2 and 1,6 positions, as there were no real single or double bonds in his structure. Whatever be the thing, in the development of modern chemistry, these structures and these concepts were rejected. And now we want the present day position of the structure of benzene. It is very interesting. From spectroscopic studies, you know spectroscopy? From spectroscopic studies and X-ray diffraction or electron diffraction studies, we get the following information about benzene. It is very, very important. All the 6 hydrogens and carbons are planar. That is a wonderful thing. Up to this time, there was no explanation for the planarity of benzene, but now we know that in the development of modern science, we know that In the light of modern developments, we can say that there's hydrogens and carbons in the planar structure. 6 carbon atoms are arranged at the corners of a regular hexagon, and carbon bond angle are 120 degree. These are the observations obtained from modern studies. All 6 carbon bonds are equal in length, that is between single bond and double bonds. Actually, you know what is the CC single bond length? It is 1.54 angstrom in ethane. And what is the double bond length? CC double bond length? That is 1.33 angstrom in ethylene. That is CH2 double bond CH2. But actually, in benzene, there is no single bond, there is no actual single bond as in ethane, and there is no double bond as in ethylene, but the bond length is 1.397 angstrom. There is a special type of bond present in benzene. That's why we are telling all 6 carbon bonds are equal in length, 1.397 angstrom. Okay, next is, what about the heat of hydrogenation? The enthalpy change associated with the hydrogenation of benzene. Actually, it is lower than that calculated theoretically for Kekule structure by approximately 36 kilocalorie per mole. The same difference of energy is observed in actual and calculated values of heat of combustion also. Now, that means nowadays there are 2 explanations for the structure of benzene based on the studies we have just seen. That is in the light of spectroscopic and X-ray diffraction studies. There are 2 explanation for the structure of benzene. We know theoretical chemistry about the structure of atoms, structure of molecules, etc. Similarly, in the case of this benzene also, there are 2 types of studies. Number 1, there are 2 types of explanation. Number 1, as usual, we know valence bond method or resonance method, and the most interesting one, that is molecular orbital method, that is VB method and MO method. That is VB method and MO method. So first of all, you take the resonance structure of benzene, that is based on valence bond method. The actual structure, that is resonance hybrid, is intermediate. We can explain the structure of benzene by using so many resonance structures. So what is resonance? The structure of molecule is intermediate between the forms represented by the limiting structures. Actually, many limiting structures are there. So actual structure is between the limiting structures, or in other words, we can say the molecule is a hybrid. That is known as a resonance hybrid of what? Of these resonating limiting structures. There are many resonating limiting structures, but the actual structure of the molecule is the resonance hybrid. Such a molecule cannot be represented diagrammatically in accordance with the usual valency rules of classical structural theory. Therefore, to represent such a molecule, the limiting structures are written and double-headed arrows are placed between them to indicate the resonance. Double-headed arrows are there between the structures. However, these limiting structures or canonical forms, limiting structures are otherwise known as canonical forms. These limiting structures or canonical forms do not correspond to any real electronic state of the molecule in an excited form. That is ground state. Clear now? These limiting structures or canonical forms don't corresponding to any real electronic structure. It's a canonical form itself. It is not real structure of benzene. So you see, this benzene is a resonance hybrid actually. Benzene is a resonance hybrid actually of what? Of the following limiting structures. So you can see the limiting structures of benzene. Actually, benzene is the resonance hybrid of these limiting structures. You see the first one? You see the double-headed arrows between these forms? Okay, that is the method. That is the method of representation. And you see the structure 1 and 2. These 2 are familiar to you. Can you say these structures are? These structures are Kekule structure actually. Then structure 3 to 5, 3 to 5, they are called Dewars structure. Dewars structure actually. Dewars structure. The structures 3 to 5 are called divar structure. And a number of dipolar structures are possible. A number of dipolar structures are possible for benzene. However, Kekule forms are more stable than either divars or dipolar forms. That is very important. Whatever be the thing, so how many representations are there, but Kekule forms are more stable than these forms. Okay, that's the importance of Kekule form. That's why, as an approximation for writing most of the reactions and properties of benzene, it may be written in Kekule form actually, even now. Okay, I think it is clear to you now. And one more thing, this predominance of Kekule forms are having 3 alternative single and double bonds explains the additional reactions of benzene and also the equivalence of all the 6 hydrogens. This predominance of Kekule forms having 3 alternative single and double bonds explains the addition reactions of benzene and also the equivalence of all the 6 hydrogens. Okay. Due to the resonance among these limiting structures, it is to be expected that all carbon to carbon bond lengths must be equal. Therefore, it must be between that of the pure single and double bonds. And this explains the observed carbon to carbon bond length. You know, what is that? 1.397 angstrom of benzene. Clear? One more thing, resonance can occur in a molecule if it is planar. No doubts. Okay, thus all the carbon and hydrogen are expected to be planar. Clear? Finally, a resonance hybrid is always more stable than any of the limiting structures. These things are very helpful to us to study the structure of benzene. Thus, benzene, which is a resonance hybrid, that is expected to be more stable than the contributing Kekule structures. Clear? Okay. The difference of energy between the resonance hybrid and its limiting structures is known as, we know resonance, and this difference in energy between the resonance hybrid and its limiting structures is known as, what is that? That is called resonance energy, and it's the measure of stabilization of the molecule also. Okay, the greater stability of benzene molecule is proved by the observed and theoretical values of hydrogenation. We have discussed that. Okay, this stability and absence of real double bond in benzene molecule explains its tendency to undergo substitution reaction rather than addition reaction. The addition reaction will tend to make the molecule non-planar and thus inhibit the resonance. Clear? On addition reaction, the molecule become non-planar because on addition we get saturation. If the molecule is getting saturation, the structure is not planar because it become tetrahedral. So planarity may lose. Planarity will not be there. The planar structure and resonance are related if addition predominates, vanishing of planar nature of the molecule, and a tetrahedral nature is obtained, a three-dimensional nature is obtained. That means valence bond method could explain many things actually. But some limitations are there for the valence bond method. So we want a modern concept that is called molecular orbital methods. According to modern approach, benzene structure is on the basis of MO theory. Usually a carbon involved in the double bond formation is in dash hybridization. You know what is hybridization in double bonds? sp2. Here also the carbon is in sp2 hybridization. By the way, what is hybridization? The process of intermixing of 2 or more atomic orbitals having different energies and shapes, resulting hybridized orbitals having identical shape and energy. So here, in benzene, the hybridization of carbon is not sp3, not sp, but sp2. If we try to write the Kekule structure on the base of MO theory, then each of the carbon atom in benzene must be in sp2 hybridization. There is no excuse. The 3 hybrid orbitals of each of such carbon atom are in the same plane actually. The 3 hybrid orbitals of each of such carbon atoms are in the same plane and forms 2 sigma bonds with 2 other such carbons. Okay, on either side by coaxial overlap by hybrid orbitals and 1 sigma bond with the s orbital of hydrogen. Clear now? You see, 3 hybridized orbitals are there. Out of that, 2 are overlapped with 2 carbon atoms. One sp2 hybridized orbital overlaps with the s orbital of hydrogen to form a sigma bond in a triangular manner. The bond angle expressed is 120. No doubts, because sp2 hybridization. So how many sigma bonds are possible now? 12 sigma bonds are possible. Clear? And what is the shape of carbon-carbon skeleton? Carbon-carbon skeleton obtains hexagonal shape. Here all the carbon and hydrogen are in the same plane. No doubts. You know the atomic number of carbon. The subshell electronic configuration 1s2, 2s2, 2p2 in the ground state. But in the excited state, what happened? One of the 2s electron may jump to 2p. We have discussed that the hybridization is sp2. What about the third p orbital? The third p orbital consists of 1 electron. Clear now? In the excited state, 3 p electrons are there. 2 p orbital and 1 s orbital undergoing hybridization, sp2 hybridization, and remaining 1 p z orbital is there, that consists of 1 electron. This unhybridized p orbital lies perpendicular to the plane of these 3 hybrid orbitals. Clear? This perpendicular unhybridized p orbital can overlap in a sidewise manner or parallel manner to the same type p orbital in the adjacent carbon. Okay, and what will be the result of that type of overlapping? Pi bonds. P orbital at any carbon atom can overlap with either of the p orbitals on the carbon at its left or right. Possibilities there, either to left side or to right side. That means there is an unhybridized p orbital that can overlap either to the p orbital present in the left side of the carbon or to the p orbital present in the right side of the same carbon. And there is a probability of both types of overlapping being equal. This results in the continuous overlapping as shown in the figure. There is a chance for continuous overlapping. This leads to what? This leads to the formation of 2 continuous or delocalized pi electron clouds, one above and the other below the plane of the hexagon of 6 carbon atoms. It is just like what? It is just like a sandwich. Clear? The 6 pi electrons are delocalized over all the 6 carbon atoms and molecular orbital is polycentric. Is clear? Not monocentric, not bicentric, but these 6 pi electrons are delocalized over all the 6 carbon atoms. These pi electrons are delocalized over all the 6 carbon atoms and the molecular orbital is not monocentric but it is polycentric. Clear now? The energy of these 6 delocalized pi electron is less than 3 pairs of localized or isolated pi electrons. That means that is present in either in alkenes, trienes, tetrienes, etc. Now you can say there is a difference between the delocalized pi electrons and isolated or localized pi electrons. Okay, in certain alkenes you can see isolated pi electrons as well as certain localized pi electrons. But there is a difference between these localized or isolated pi electrons and the 6 delocalized pi electrons present in benzene. In which sense? In the sense of energy. The energy of these 6 delocalized pi electrons is less than the 3 pairs of localized or isolated pi electrons and therefore the molecule is highly stable compared to the alkenes. Okay, this difference of energy due to which the molecule is stabilized is called delocalization energy. Once again, in certain molecules, in certain alkenes, isolated double bonds are there or 3 pairs of localized double bonds are there, but there is no chance for delocalization. But in benzene, there is a chance for delocalization. Even though there are 3 pairs of pi electrons are present in certain organic compounds, these compounds are not stabilized. But benzene is highly stable. Okay, due to what? Due to delocalization. That means there is a difference in energy due to which the molecule is stabilized. Clear? This difference in energy is called delocalization energy. Okay, that means MO picture of benzene explains planarity of the molecule. You know, sp2 hybridization, bond angle of 120 degree. Due to sp2 hybridization, we get triangular molecular parts. That triangle consists of what? 120 degree. Then equal carbon-carbon bond lengths, because equal chance for sidewise overlapping. So equal carbon-carbon bond lengths and stabilization of the molecule, that is delocalisation energy. Thus MO method is very, very effective. The pi electrons are delocalized, and forms electron clouds on either side of the plane of carbon atoms. Benzene can act as a source of electrons actually. Therefore electrophilic reagents will attack the molecule more readily. To preserve the delocalization and corresponding stability, the molecule will tend to undergo substitution rather than addition reaction. Now we got the answer why substitution rather than addition with the electrophilic reagents. Due to the delocalization of pi electrons, benzene is represented by a particular drawing like this. Dotted lines are put in here, or a continuous inscribed circle as shown in the figure. There is a representation of benzene. I think now you got the exact picture of benzene. Actually, it is a developmental task. Many scientists contributed to explain the structure of benzene. The most important thing is Kekule's explanation, and again we got the concept of resonance, that is valence bond method. Resonance can help us to a very great extent, but the most important one is MO method, that is molecular orbital method, that is based on hybridization. And now we got the exact picture of benzene. We can see the reactions later. So study well, prepare well, go ahead in the field of chemistry. So think about the chemical developments, subscribe the channel, SPCL Bond. Thank you.